Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture. So in the preceding lectures we have seen how properties like linearity, time invariance and causality of a system play an important role in enabling us to play around with certain properties and to infer about the response of the system for a given input. So this is in general not a trivial question, of course, because for different inputs your system will have different kinds of outputs. Now only when it is linear, we have seen, we can play around with this and we can figure out, based on our knowledge about the response of the system to a certain number of signals, we can cook up the response for a linear combination of those possible input signals, right. We have also seen the importance of properties like time invariance and especially its role in enabling us to ascertain the causality of a system given that a system is time invariant. Now where does all of this lead us to? Towards the end of the last lecture we did mention something called Laplace transforms, which I am sure many of you are already familiar with in some earlier course on mathematics or maybe signal processing. Nonetheless, in this course on controls we shall look at Laplace transforms in probably a different light to what you have seen thus far. So without further ado, let us focus on some basics about Laplace transforms, such as the definitions and properties of Laplace transform as they are visible on the screen here. So you can see that for functions f, f1, f2, g, which are defined over the domain from 0 to infinity, which typically is basically all the possible values of time to some real value, and functions have to be piecewise continuous as well, then we see that the Laplace transform of such a function given by big F, if the original function in time domain is small f, then the Laplace transform is given by big F and it is defined in the manner shown in the screen, that is integration from 0 minus to infinity f of t e to the power minus st dt. At first glance you might think that we might be making too fine a point on this lower limit of the integral, right, the 0 minus. In some books you might see 0 plus. Now these are actually, although not by much, but slightly different notions of Laplace transform. To be very precise, the definition that you see before yourself in the screen right now is a one-sided Laplace transform. The both-sided Laplace transform would have a lower limit of minus infinity. Over and above that, we generally denote this Laplace transform by a subscript followed by following L, that is L minus rather than L plus, okay. Now why is this important? Perhaps at this point it might be a bit premature to discuss that, but we shall shortly see, maybe towards the end of this lecture or in the next lecture, as to why this 0 minus and 0 plus is so significant. Remember, we had motivated our study of Laplace transforms in the last lecture by saying that Laplace transforms will aid us in solving differential equations that are linear and time invariant in quite the same manner as logarithms help you in carrying out multiplications of large numbers, okay. So we would point it out to you at some point that this solution of differential equation is where the difference between 0 minus and 0 plus as the lower bound of that integral, lower limit of that integral, is going to make a difference. But more on that later. So for now let us focus on some of the important properties of Laplace transform. The linearity property is quite evident from the fact that the integration itself is a linear operation, right. So if you take two functions f1 and f2, combine them linearly by alpha 1 f1 plus alpha 2 f2, then of course by the definition that's before you right now, it's obvious that it's linear. Then there's something called time delay. We've already seen this, we've denoted this by a shift operation in the previous lecture when we were dealing with time invariance, if you recall. So that same sigma t here instead of tau, okay, so if you take a shifted version of a signal and want to take its Laplace transform, provided you know the Laplace transform of the original signal, you just have to multiply it by e to the minus st, alright. Then there comes the derivative. This is very important again in view of the fact that Laplace transforms will be widely used mostly to solve differential equations. So it's only fitting that you know what the Laplace transform of the derivative of a function is, provided it's already known what the Laplace transform of the original function is. So remember, as I told you in the previous lecture, there are certain standard functions for which you know what the Laplace transform looks like. There's actually a table. In any standard textbook, you'll find that there's a table of Laplace transforms and inverse Laplace transforms in, again, the same manner as you have a log table and an anti-log table, right. Finally, we have on this page, you see the integral of f, right, just like you have the expression for the derivative of f and its Laplace transform. Similarly, if you integrate f of tau over the interval 0 to t and you want to find out its Laplace transform, what you need to do is you need to divide by s the Laplace transform of the original signal f of t. You might see there's a footnote there where we've also defined what the inverse Laplace transform is like. Needless to say, this looks very challenging and cumbersome. Luckily and thankfully, this is not the formula that we shall be using in order to obtain the actual Laplace inverse. But more on that again later in some later lecture probably. Okay, then there are certain other properties which we shall see in this lecture why they are significant. One is the convolution. So it turns out that convolution operation in the time domain defined by so, where you integrate from minus infinity to infinity f of tau, g of t minus tau d tau, right. The Laplace transform of this convolution of two functions turns out to be the product of the Laplace transforms of the individual functions. Again, this will be important. Then there's something called Dirac delta. Of course, in many standard textbooks they call it a delta function. I take certain exception to the use of the term function very loosely, because in reality this is something called a distribution. And in fact this is not a function in the conventional sense, mostly because at this point it suffices to know that normally a function is defined in this manner. You have a domain of the function, okay, you pick out some element from the domain of the function, pass it through the function, and you get a value which belongs to the range of the function. Dirac delta is not something that's defined in that manner. Rather, as you can see from here, it is defined by what it does to a function, okay. So Dirac delta is not defined by you pick out something from the domain, pass it through the Dirac delta and you see what's happening in the range, right. Rather, you see the action of the Dirac delta on another function, what it does to it, and that's how it is defined. There are some alternate definitions too, but this is primarily a subtle difference. So I wouldn't call it a delta function, although most textbooks would probably do so. Then IVT is basically the short form for initial value theorem. So for example, if you have f of t and you want to find out what f of 0 plus is, again this is an important parameter to find out, as we shall see when we see how to solve differential equations. Then it turns out that if you know the Laplace transform of f, that is f of s, you can simply pass it through the limit s tending to infinity s times fs, and that's going to exactly give you f of 0 plus. We shall see some short sketches of the proofs of some of these results, okay. Of course, you have to mind the caveat here, which is provided the LHS exists, that is no impulses or their derivatives exist at t is equal to 0. There are ways of handling this even if there are derivatives and impulses, but that's somewhat a brute force sort of a method. For the most cases we'll assume that there are no impulses and the derivatives at t is equal to 0. Then there's the final value theorem, which of course also comes with a caveat, needless to say, that provided the LHS, that is f of infinity, exists. So for a divergent function there is no question of settling down to a final value, same for an oscillatory function. So therefore f neither diverges nor oscillates, okay. So it actually has some steady value as t tends to infinity, right. That is a standing assumption. In that case you can similarly evaluate the final value by knowledge of the Laplace transform of f itself. How? Pass it to the limit s tending to 0, s times f of s. Then of course there are those three properties like time domain multiplication, complex shift and time scaling. These are standard properties that you will find in any textbooks, and I am pretty sure if you have gone through a maths course that has covered Laplace transform, most of you are already familiar with these properties. Nonetheless, this is just a refresher. And finally here we have some standard Laplace transforms. So by 1 we denote the unit step, right. So functions are only on 0 to infinity, so it is a unit step, that is the 1. The Laplace transform is 1 over s. Then you have t, which is basically the straight line, it is a ramp. The Laplace transform is 1 by s squared. Then you have the exponential e to the at, whose Laplace transform is 1 by s minus a. Similarly you have the Laplace transform of the sinusoid, the cosinusoid, and also a sinusoid or a cosinusoid enveloped by an exponential, right. So these are some important functions, and it turns out that even knowledge about these few functions and their Laplace transforms will enable us to get very far insofar as the precincts of this course are concerned, right. So with that we end a short refresher of Laplace transforms, and with that we will begin discussing some important properties in today's lecture and see some of those results that we have already seen in some new light. Hopefully this will shed some new light on what you already know. So at the beginning, if you indulge me a bit, I will discuss something which may not at first glance seem very relevant to what we have just seen so far insofar as Laplace transforms are concerned, but shortly we shall begin to see the connection, I promise, right. So let us say we take something called the unit pulse function, okay. Just indulge me a bit and carry on with me on this journey. How do we define a unit pulse function? The sketch of the function would look something like this, okay. So if this is the time axis, this is magnitude of 1, alright, and this is the pulse function. So this is, let us say this is still t0, this is the time axis, and this is what the unit pulse function looks like. So how do we describe this? For example, if you want to describe this mathematically, here is how we would describe this. So remember that the unit step, let me mark that on the side here, the unit step is defined in this manner. I would define it as 1 of t, and it is equal to 1, alright, it is equal to 1 for all t greater than 0 and 0 otherwise, alright. Right. So the unit step looks something like this, right. Right. So this is what unit step looks like. Now if I want to compose this unit pulse in terms of unit step, alright, how do I go about doing this? So let me just correct that a bit, right. So this is greater than or equal to, yeah, just a subtle point, but it is important, right. So this how do we then define this? Think of this composition. So let us say you have a unit step that is going on this way, and then at t naught you start another function, negative step, alright. So then the resultant of these two would obviously be something like this, is it not? Yeah. So this is basically what we are looking for. This is the pulse, right. So how do we write that mathematically? Without further ado, let me just write it down in, okay, Let me just write it down here. So this is nothing but the unit step, and from that you subtract a delayed or a shifted version of the same unit step, right? Okay. So how do we describe this in other words? This is nothing but characterized by the following. So it is 0 for all t less than 0, it is 1 for all t satisfying this condition t naught, and it is again 0 for all t greater than t naught, right? No questions about this. This is exactly how it is defined. Now suppose you want to take the Laplace transform of this f of t. Yeah, how do we take this? We know that the Laplace transform of this is of course 1 over s, right? And what is the Laplace transform of this? This also we know, it's the delay. We've just seen this property, right? So this is what it is. In other words, we can write this as 1 minus e to the minus st naught over s, right? So we'll just bear that in mind for the time being, that the let me just write that down. So the Laplace transform of f of t is equal to this. This is the point to be taken home from this particular slide and to be remembered for reference later. So now let's look at some of the properties. As I promised, we'll see. This will actually help us later on, but first let us look at some of the properties. So for the time being, just remember this result, keep it in the back burner, slowly burning till we need to revisit this. Okay, we are sort of trying to cook up the recipe for a lot of things. Let's take a general case, okay. So let's say there is this function r, r of t, and you want to take the Laplace transform of the derivative of r. So how do we take that? From the definition, we are not doing anything but using the definition. Remember the 0 minus to infinity e to the minus st, right, d dt of r of t dt. This is nothing but, once again, as we have already seen, please refer to those properties I have just discussed in the slide, alright. So let us mark this as equation number 1. Let us mark this part as equation number 1. Now, if I focus my attention on this part, just this part, alright, and what am I going to do with that part? Let us say I just split that integration up. So I will not write the entire thing, I will just say, let us just split that up from 0 minus to 0 plus, just this part, this part dt, and we just split this integration up into, and 0 plus to infinity, that same integrand dt, alright. And we know that this is equal to s fs minus f of, sorry, this is not, let's not call this f, let's call this r, yeah, because after all we are choosing the signal r, so it's only fitting that we call it r instead of f, and we don't want to confuse this with the f which we've used to define the ramp in the previous slide. So this is true for a general signal, right. So this also comes from the previous line, pretty straightforward, we just split up the limit of the integration, alright. What about the next line? So what can we say about this? Look at this particular, I want you to focus on this particular portion. What can we say about this? You see, when you are taking this limit from 0 minus to 0 plus, what can you say about this e to the minus st? This is unity, isn't it? I mean, in the neighborhood, in such a small neighborhood of 0, this is as good as 1. So therefore it is just an integration of the differentiation, which is just the antiderivative of this. So I can obviously write this as 0 plus r of 0 plus minus r of 0 minus plus, let me now write that integration, e to the minus st d dt of rt dt 0 plus to infinity is equal to s r of s minus r of 0 minus. Okay. And now you can see that I can actually cancel this out from both sides, which then leads me to conclude that this s times r of s is nothing but this integration plus r of 0 plus. Now suppose I pass this through a limit, alright. So remember how did I start all of this? I started this, of course this step you have to verify. This is actually a property of the Laplace transform, but this is also not very difficult to derive. If you just use integration by parts on this once, you can see that this immediately follows, alright. All that we have done is we have taken this left hand side, and instead of just directly integrating by part this time, we have just split up the limits and we have written this part separately. Why are we doing this? Because in general we are trying to account for, so the question is why are we doing this? That is because we are trying to generally account for any discontinuity in the signal r at t is equal to 0, okay. If there is discontinuity, then these two are not one and the same, alright. So that is why we are actually also choosing this minus, 0 minus, and this will also be clear over the course of time as we discuss more and more topics that will show us the stark difference between considering 0 minus and 0 plus as the lower limit of this integral. Nonetheless, as I promised, we shall keep all that in the background for the time being and just focus on this, okay. Just to show you that even by considering 0 minus, the main results that you might be already aware of do not change, because even if you have seen 0 plus in your familiar texts, yeah, I want to assure you that even with 0 minus the results hold exactly the same. I mean, the reason behind this discussion is you might feel that, you know, when we have defined the Laplace transform as the limit from 0 minus to infinity, then shouldn't the initial value theorem also dictate that this becomes 0 minus, but it is not so, because you can see that this 0 minus, r at 0 minus cancels out from both sides, and whether you take this limit from 0 minus or 0 plus, the initial value theorem is always going to give you r at 0 plus. If it seems like too fine a point and I am harping too long on it, again please bear with me, because we will see shortly when we deal with functions that are discontinuous at t is equal to 0, yeah, then this assumes significance. Okay, enough said, let us pass this through the limit. So let us use the limit s tending to infinity on both sides. If you see, if we pass this through limit on both sides, this is independent of s, this term r of 0 plus, so it does not matter to this. Of course, what happens to this? So if you pass this through limit s tending to infinity, right. So you see that on the left hand side you still have the 0 plus remaining. What happens to this term? You see, as s tends to infinity, this goes to 0, and so therefore this term vanishes, and on the right hand side you will be just left with limit s tending to infinity s times r of s, which is nothing but your initial value theorem. And finally the point I was making, the fact that irrespective of whether you have chosen your lower limit of the integral in your Laplace transform definition as 0 minus or 0 plus, the initial value theorem is always going to spit out the value of the function at 0 plus, not at 0 minus, okay. Alright, so in case you have discontinuities, the initial value theorem is not going to tell you the value at 0 minus, okay. That is something to be remembered. Okay, so we have seen two things already. One, we have seen this unit pulse. Two, we have seen that what the significance of this initial value theorem is and how it does not change the expression whether you take the the Laplace transform from 0 minus or from 0 plus. Next we are going to look at this Dirac delta. As I said before, I will not call this a function, just call it Dirac delta. Okay. So how do we approach this Dirac delta? Let us first look at something we already know, that is the pulse we have already discussed. So suppose you have something like this, alright, a pulse of magnitude 1 over delta from the instant t1 to t1 plus delta. Okay. So the area of this pulse is unity, the magnitude, the peak, the amplitude is 1 by delta. Okay. So let me define this function delta of t minus t1 as equal to, so this is basically this function. So one way of defining this is clearly, if you look at how we have defined the Dirac delta, the unit pulse, it would immediately follow that the Dirac delta can be defined, or the approximation of the Dirac delta, we have not yet seen that this is the Dirac delta, the approximation of the Dirac delta can be defined by this expression. Alright. Okay. I wonder what happens as delta tends to infinity. Pictorially, of course, you can see that this keeps getting narrower and narrower and the peak starts climbing higher and higher. So as you make us choose a smaller delta, for instance, because the area is fixed, you choose an even smaller delta and maybe you will get something like this, right. So that is what happens. Pictorially you can see this, but theoretically what happens here? It is apparent that this will actually approach, as this delta tends to 0, of course it is not going to be on the center, it is going to approach to the left. So as this delta tends to 0, it is going to be like a Dirac delta at t is equal to t1. So clearly as delta tends to infinity, this delta of t minus t1 approaches Dirac delta. Okay. That I hope is at least clear. But what happens in the limit delta tending to 0, in the limit delta tending to 0, the Laplace transform of delta t minus t1 is what we are interested in, is given by, and this is the interesting bit. What happens? You see, excuse me, you see that if you take the Laplace transform of this, this is limit delta tending to 0, 1 over delta, what you have here is e to the minus st1 minus e to the minus st1 minus plus delta, right. So you can pull out this e to the minus st1 and then what you have is 1 minus e to the minus delta over delta limit delta tending to 0. Of course, this is unity, right. So therefore, what you have is e to the minus st1. So at least that we have seen. An important property of this Dirac delta is of course the shifting property, so much so that this is also used to define. Now of course, if you define the Dirac delta in this manner as an approximation in this manner, then you should be able to derive. So if this is your definition, then the shifting property needs a derivation, remember. But on the other hand, if the shifting property is how you are defining the Dirac delta, that is how it acts on another function is how you are defining this, then of course this needs no derivation, it is by definition true, right. So you should be able to see that the two definitions are actually equivalent. So what does the shifting property say? The shifting property says that if you take any function f of t, right, and pass it through this like a sifting or sieving operation that is going on, then you basically it is going to pick out the value of that function at t is equal to t1, alright. So this is a very, very important property. Okay, so I believe that this should bring some or rekindle some memories that you might have from an earlier course that you might have done on mathematics or signal processing, right. The sifting property is a very, very, in fact it would not be an overstatement to say the fundamentally most important property of this Laplace transform of the Dirac delta function, alright. So now we are going to look at something interesting, and this is going to be more relevant. Now things will start getting more and more relevant to our line of inquiry or pursuit. What is that? So consider any signal, okay. Now that we have seen some of those basic properties, we have seen a unit pulse, we have seen how to cook up the Dirac delta using the unit pulse. In between we have also seen this interesting property of this initial value theorem and the fact that the 0 minus makes not a difference to it. Then we have seen the sifting property of the Dirac delta, alright. Now we are going to see how to express any signal as a train of delta, okay, of Dirac delta. How do we do that? This is very important because this is going to eventually allow us to describe the input output behavior of a linear time invariant dynamical system. Okay. So again, as before we start with a sketch, let us take a signal, say u of t, okay, some arbitrary signal like this, and like you might have seen in Riemann integration, right, you split up this into, my drawing is not very good, but these are equal intervals, okay, even if they do not look like that, right. It is exactly like you did the partitioning for Riemann integrations, right, the same thing, okay. So you split them up, but if you now focus on each of these individual parts here, what are these? These are nothing but pulses themselves, no. This is like, for instance, a pulse, right. So let us say that we have split this up from say t0, then t1 till let us say tk, okay. This is the time axis, and let us say delta is equal to, we are just calling this interval, this even interval, this equal intervals, that is, as any tr minus 1 for all r, for all integral r, for all integer values of r, okay. That is all this means. So it is even intervals, equal intervals, that is, alright. So now we can actually cook up another function u of delta from u. So u of delta t1 for instance, or let us say ti, t0, t1, so similarly there is some ti here. So let us say we want to find out what is u delta ti. What function is that u delta ti? Let us say it is just this function, this pulse here. Now once we already define this as a pulse, we are approximating this as a pulse, that is, we know how to express this pulse. It is very simple, no. What is the magnitude of that pulse? What is the amplitude of that pulse? It is exactly the value of u at ti, right. So this is the amplitude of that pulse, right. And how do we express that pulse? We have seen that we can express this pulse. I will like to take you back here. Remember, this is basically a pulse of amplitude 1 over delta. So if you want to make this a unit pulse, you have to multiply this by delta. Remember, this we saw was a pulse which could be approximated to the Dirac delta, right, but the difference is that this pulse had an amplitude 1 over delta. Here we want a pulse whose amplitude is u of ti. So now when we multiply this over with t minus ti, this pulse, we also need to adjust and multiply with this delta, because this overall thing is going to be a pulse of amplitude unity, and when multiplied by u of ti, it gives us exactly the pulse of amplitude uti, alright. So this is basically one individual piece, one individual slice. So now combining all of this, let me cook up an approximation of ut, which is given by u bar of t. So this is what? An approximation of ut. And we can clearly define this through this summation, this infinite summation I is equal to 0 to infinity, of course countably infinite, u of ti delta delta of t minus ti times delta, right? We have seen that. Okay, what about the next step? So then excuse me, so then let us say delta, we allow it to tend to 0 once again as before. Clearly as you tend delta to 0, this approximation error between u and u bar is going to get smaller and smaller, yeah, that is essentially the idea. We want to minimize the approximation error, and for that purpose we will let delta tend to 0. So if we let delta tend to 0, then clearly at some point this approximation error can be nullified. So we can write this as limit delta tending to 0, and that same summation that we have written, u of ti delta delta of t minus ti times delta, alright. But this is nothing but something we already recognize, right? This is basically an integration, is it not? When you are letting this delta tend to 0, this is nothing but d tau. So we can easily replace this by the integration operation, yeah. It might appear a little hand waving at this point, but as we are letting delta tend to 0, clearly this approximates the Dirac delta and gets closer and closer. This delta is like the d tau, yeah, and this u of tau is basically the running variable then, right. Alright, so we have seen that this is one way of expressing any signal, alright. But what is our motivation behind doing all of this? Why are we doing this in the first place? At this point let us focus on that. Essentially what we want to find out is, suppose you apply this input ut to a linear time invariant system which is described by G, then what is the output? That is our question, right. Can we express this output in terms of the input, right, and how does linearity and time invariance and all those properties help us here? So now that we have described this u of t in this fashion, we should go ahead and try to do this, shouldn't we? So then we know that y of t is nothing but G acting on u of t. Remember in the previous lecture we had removed this third bracket, yeah, for brevity, but we bring this back now. So what is this? This is again going back one step further, at least let us say we want an approximation of this. So we want to find out at least the response of u bar, response to u bar, okay. So then we write this as nothing but that same summation I is equal to 0 to infinity u of ti delta delta of t minus ti. We like a discrete sum because that will help us in pushing through the property of linearity. We shall see that. Now notice in this sum, if G happens to be a linear system, then the action of G on a sum of these type of signals is the same as the sum of the action of G on individual signals. That is what linearity is. And here what are the scaling factors, what are the constants? Remember u of ti is held constant over the interval from ti to ti plus delta. Delta is also a constant. So we pull those two fellows out, yeah, we can pull those two fellows out and we can push G inside, right. How are we going to do this? Let us take one step at a time. So this is nothing but, okay, let me retain the third bracket, does not matter, g over u of ti 0 to infinity u of ti delta delta of t minus ti times delta. Now remember that this summation, I can insert this g inside the summation like this only because this g is smooth, and the second point to be noted here is that this delta is going to be a constant. So when we later on transform this to an integral, this delta will be playing the role of dt or d tau, whatever the running variable is. In fact, it will be d tau, as we shall see, okay, right. So therefore we have y bar of t, which is the approximate response, yeah, and here is where the smoothness of g is very important, yeah, because we are taking infinite sums, just to point out, okay. I am not asking you to prove this or like get into the depths of that, what the smoothness of g is, but because we are taking these infinite sums, the smoothness is what we had concerned ourselves with in an earlier lecture. Okay, so what does that tell us? We can pull out this uti outside this g and also this delta outside this g. What will happen then if we once we've done that, we can write this as summation I is equal to 0 to infinity, and let me just write this as g delta t minus ti, yeah, delta times u t minus, sorry, that was ti, yeah, delta times u ti, right. And now let delta tend to 0. So if we let delta tend to 0 now, what happens? This reduces to an integral, but even before that, notice that what does this tell me? It tells me that if I know how my system responds to each of those individual pulses, yeah, I can cook up my overall response of the system, right. That is the beauty of linearity. That is why we were so hung up on this so called property of linearity, alright. So now before we get into this, passing this through a limit, let me just make a side note here, and I will say that g of delta delta t minus ti, this is an important thing. This is basically response of the system, yeah, response of the system at time t for an input, yeah, what sort of an input? Input delta delta applied at time ti. Okay, this is how this quantity is defined. Okay, notice that because implicitly there is this notion of time invariance, because it is time invariant, therefore only this difference between t and ti matters here. Okay, so it is independent of whether this t and ti are respectively 105 and 100 or 1005 and 1000. Okay, it does not matter because it is time invariant and linear, therefore it is only the difference between the application of the input, the instant of application of the input, and the instant of observation of the output that matters. Okay, so all these properties that we focused on in our earlier lectures, they begin to come together in this. Okay, we see the pieces in the puzzle coming together. Okay, so now getting back to this limiting business, if we pass this through a limit, we can clearly see that this approximation error and this y bar can be removed to and replaced by y, because this approximation error can be nullified. So then we can write this as 0 to infinity g of t minus tau, yeah, u tau d tau, alright, for, remember from this notion, for t greater than tau, alright. Yeah, so that is essentially what this is. Now clearly by the same token as this was important in the approximate version, now the variable or the object of our interest is this, because this is essentially what is capturing whatever the system is doing to our input signal, right. So this is very special, this g of t minus tau, this is basically defined as the impulse response of a system, impulse response of the system, okay, at t due to delta t minus tau applied at tau. What that means is, if you apply the Dirac delta at the instant t is equal to tau, and at some later instant, let us say t, you want to observe the effect of that, then it is this g of t minus tau that tells you exactly what that effect is. So in other words, if you know how your system responds to these impulses applied at different time instants, because you can cook up your input signal using these trains of impulses, you can basically cook up the response to any signal, okay. The critical piece in this puzzle is understanding this g, okay, this g of t minus tau. That is why this is very important, the most important quantity in fact, insofar as our studies will be concerned. Okay, next, not to make too fine a point on this, but how do we go about describing this g in an alternate fashion? Is this the only way to capture the behavior of the system, of the linear time invariant system, through this complicated looking integral at the end of the day? There should be some simpler way. In fact, why after all were we studying these Laplace transforms to begin with? Is there some relation to the Laplace transform? Is there some way we can massage this to conveniently leverage on some properties of this in the Laplace domain? So in our bid to do that, the first thing we do is we define something called a transfer function. What is a transfer function? Quite simply put, now that we have seen what this impulse response is, the transfer function is nothing but Laplace transform of the impulse response, okay. So to quickly recapitulate what we have seen in this lecture so far, we've seen first the unit pulse, then we took a brief digression and we saw that this initial value theorem does not change by changing the limit of the lower limit of the Laplace transform from 0 plus to 0 minus. Then we focused our attention on the Dirac delta, its approximation, and how we can make that approximation converge to the actual Dirac delta by letting delta tend to 0. Then we have seen the shifting property by which some people also define the Dirac delta. Thereafter we have seen how to express any signal as a train of Dirac delta functions, and after doing that we have seen how we can study the effect of any linear time invariant system on a signal when we have cooked up the signal using Dirac deltas. How? We have seen that if we understand how the system acts on this Dirac delta, and that is captured by the so called impulse response, then we can actually cook up the output, that is the response of the system to any input. Okay, this integration might seem familiar to you, we have already seen this in the earlier part of the lecture. This is the convolution integral, okay. So now finally, after having seen all of this, we want to see the connection to whatever we have studied so far in the time domain to Laplace transform that we have seen in the earlier part of this lecture, and we see, quite simply put, that whatever this g is doing in the time domain with all these integral and convolution integral and stuff, the same thing can be captured by a transfer function if we define the transfer function as the Laplace transform of the impulse response. Okay. So let us quickly take a look at this and then we will wind up with this transfer function description today. Okay. So let us say we have y of t as we have seen here from the previous slide, 0 to infinity, g of t minus tau, u of tau, d tau, alright. Now suppose at this point we impose, suppose system is causal. So if system is causal, then what do we know? The response at time t cannot depend on the input for any time instant greater than the time instant t, isn't it? So whatever values the signal u tau takes for any instant greater than t will not affect this. Therefore we can safely take the limit of this integration from 0 to t. Yeah, this is what causality will allow us to do, right? Okay, once we have seen that, this is basically what you have seen most likely as the convolution integral. Okay, so we call this the convolution integral. So remember, although this looks exactly like the convolution integral, this limit can only be changed to this when the system is causal. Okay, so each of those properties that we have studied, they are indeed important. Okay, so now it is quite straightforward to see that, you know, it is just a change of variables, that g of t minus tau, u tau, d tau. So this is an observation. You can also check this, it is quite straightforward really, to check that g of tau, u of t minus tau, d tau, alright. Just replace the variable t minus tau with z and adjust the integration and the dz accordingly. Okay. So with this observation in mind, we'll move forward. So now that we've described yt, let's take the Laplace transform of yt. So what is the Laplace transform of yt? The Laplace transform of yt is nothing but the Laplace transform of whatever we've defined so far. So 0 to t, g of t minus tau, u tau, d tau, which can in turn then be written as, of course, by our observation in the previous slide, we can now replace this as Laplace transform of 0 to t, g of tau, u of t minus tau, d tau, alright. Now let us try to understand what this u of t minus tau looks like. Now suppose we assume initially everything, so this is an assumption, important to put that forward, everything is relaxed. What that means is that your u, so if this is your ut or rather u tau, because tau is your running variable, let us say this is u tau. So before t is equal to 0, it is 0. Then if you look at u of minus tau, it is going to be something like this, proceed in the negative direction of time, right. And then if you take u of t minus tau, it is going to be shifted to the right by t. So this is basically t. This is of course the tau axis, it's the tau axis, and this is the tau axis, alright. So u of t minus tau looks something like this. In other words, u of t minus tau is 0 for any tau greater than t. So u of t minus tau is basically equal to 0 for all tau greater than t, right. At least that we have convinced ourselves, if provided the assumption that the system is initially relaxed or that the input is initially 0 for all tau less than 0. Okay, if that is true, then this is also true, alright. But how does this help us? So now we are again going to change and tinker this limit. We will see later why this is important, because we want to eventually make this consistent with Laplace transform, for which the integration is defined from 0 to infinity. So now you notice that if you change this limit of this integral from 0 to infinity instead of t, it will matter not, because between t and infinity, see, for tau greater than t, this is already going to be 0. So you can already write this as u of t minus tau, because this u of t minus tau, this fellow by virtue of this property, which is also by virtue of this initial relaxation, will ensure that for all tau greater than t, this is going to be 0 in any case. So it does not matter if I extend this limit of this integration, the upper limit from t to infinity. Okay, how is that going to help? So then in the next step, we, instead of writing this L, we actually use the definition of Laplace transform. So it is basically 0 to infinity, and then we put this whole stuff inside, 0 to infinity g tau u of t minus tau d tau. Of course then you have to have minus e to the minus st, yeah, dt. Okay, what next? So then we have L of yt is equal to, we have two back to back integrations, both from the same limit, and that is the beauty of it. That is the reason why we carried out this change of upper limit, although it did not matter, but this will enable us to interchange these here. Okay, and we will see shortly how that helps. So then this is nothing but g of tau u of t minus tau e to the minus st dt d tau. Alright. Now that is nothing but, I can again make some clever, so called clever change here. So this is g of tau u of t minus tau, and then let me write this as e to the power minus s tau, and then e to the power minus s t minus tau. Yeah, the order of integration will not matter at this point, right? I can play around with that because the limits I have already made the same. That is exactly the idea behind all of this operation that we have done. Alright, so then where does that lead us to in the next step? Now you see we can take these two separately. So we can take this 0 to infinity g of tau e to the minus s tau separately, yeah, and then we can take the 0 to infinity u of t minus tau e to the minus s t minus tau d tau dt, sorry, this is dt and d tau, yeah. Now you see that in this, if you change your variables from t minus tau, if you substitute that as gamma, so that is quite obvious. What you can do here is, you can split up this integral further into integration from 0 to tau dt plus integration from tau to infinity dt, and this part will vanish. Why? Why will this part vanish? Once you understand this, the rest of it is cakewalk really. Again, due to that same property, you see, now again you take the, now your running variable is t, so u of t minus tau is equal to 0 for all t less than tau, right? We have already seen that, so we are just reiterating, and by virtue of that, if you are running your limits of t from 0 to tau, this fellow, this property will make this 0. So eventually what you will be left with is 0 to infinity g of tau e to the minus s tau, alright, and you will have here this integral from tau to infinity e to the minus s t minus tau u of t minus tau dt d tau. Now if you substitute this t minus tau as gamma or any running variable or z or whatever, you will see that eventually this turns out to be the Laplace transform in terms of that variable, right. In other words, this finally leads you to the following: integration 0 to infinity g of tau e to the minus s tau, right, and you will have integration 0 to infinity u of gamma. You can take that as an exercise, it is just a change of variables really, e to the minus s gamma d gamma, and this is, of course you can also separate this now, you can bring this d tau here. So what does that mean? This is nothing but g of s times u of s, right. Remember, we have always been talking about this, but we have always mentioned that while we were dealing with this as an operator, in our earlier lectures we saw that when we wrote this small letter and we said y is equal to g of u, or sometimes we omitted this bracket, we were very careful to clarify that this, when we write y is equal to g of u, is not a multiplication, okay, this is not a multiplication in general. But now once you are dealing with it in the Laplace domain, it is indeed just a product of the Laplace transform of the impulse response and the Laplace transform of the input. So much so that now this is what we call as the transfer function, as we have already defined as the Laplace transform of the impulse response, okay. So this is basically the transfer function of an LTI system, that is a linear time invariant system, okay. So this is how we derive the Laplace transform, that this is in essence what captures everything that you need to know about the linear time invariant system. In the next lecture we will see further how we can derive these transfer functions for different systems, especially ones described by constant coefficient differential equations, and we will see some other interesting properties. Thank you.